A água é um dos recursos mais valiosos do planeta. No campo, nas cidades e nas florestas, na agricultura, na indústria, na geração de energia e no lazer. Ela é fundamental em todos os momentos das nossas vidas. Mas a água não está sempre disponível na quantidade e na qualidade que precisamos. No Brasil, temos longos períodos de seca, enchentes frequentes e forte demanda pelo uso da água em regiões com pouca oferta. Para enfrentar esses desafios, foi criada a Agência Nacional de Águas, a autoridade do governo federal responsável por monitorar, planejar e regular o acesso e o uso das águas gerenciadas pela União. A ANA estimula a gestão participativa, que envolve o poder público e representantes dos usuários e da comunidade. Afinal, cuidar de um bem precioso como a água é uma missão da ANA e também de todos nós. Saiba mais sobre a ANA no site www.ana.gov.br.
Com apenas 8% da rede bancária na região, o Banco do Nordeste concentra quase 65% do total de financiamentos de crédito de longo e curto prazos em todos os setores da economia. O Banco do Nordeste é também o principal agente financeiro do agronegócio em sua área de atuação, respondendo por 54% do crédito rural na região. Atuando para promover o crescimento sustentável na região Nordeste, por meio de apoio financeiro às atividades agropecuárias, o Banco do Nordeste oferece linhas de financiamento com as melhores condições de mercado em diversas atividades, seja para custeio pecuário, custeio agrícola, máquinas e equipamentos, investimento, comercialização e exportação, agricultura irrigada, energias renováveis e armazenagem. O FNE, principal fonte de recursos do Banco do Nordeste, possui as menores taxas de juros do país, prazos diferenciados e bônus para pagamentos realizados em dia. Tudo isso aliado às melhores soluções, com opções de crédito diferenciadas para quem tem pressa de crescer. O cartão BNB Agro oferece crédito rotativo com agilidade e comodidade. Já com Planta Nordeste, você tem renovação automática do custeio, além de pré-custeio e comercialização. E para garantir um futuro sustentável, o FNE Sol financia sistemas de geração de energia renovável e redução nos custos de produção. O Banco do Nordeste possui soluções ideais para a atividade rural. Por meio do FNE Irrigação, apoia empreendimentos que desenvolvem a agricultura irrigada, fundamentais para o crescimento da região. E para quem quer manter seu empreendimento sempre atualizado, o banco oferece financiamentos de peças de reposição e manutenção de equipamentos e veículos. No Banco do Nordeste, o futuro é agora. São diversas soluções digitais para simplificar e modernizar sua vida, como cadastro, conta corrente, simuladores de financiamento e login digital. E os pedidos ao fornecedor no cartão BNB Agro são feitos via mobile. É o Banco do Nordeste levando o desenvolvimento digital ao agronegócio. Com o BNB Agro Inovação, o produtor rural aumenta a sua competitividade por meio da incorporação de tecnologias e inovações no seu processo de produção e de gestão, como equipamentos de agricultura de precisão, máquinas autônomas e outros. O Banco do Nordeste tem uma política específica para o agronegócio, destacando-se apoio ao desenvolvimento do cerrado nordestino, incentivo à utilização de tecnologias de convivência com a seca e desertificação, apoio à logística de armazenamento da região, incentivo para ampliação de áreas irrigadas, apoio à pesquisa e à difusão de tecnologias para o agronegócio e estímulo aos projetos de micro e mini geração distribuídas de energia por fontes renováveis. O Banco do Nordeste e a Confederação da Agricultura e Pecuária do Brasil têm parceria voltada para a realização de ações integradas, a fim de ampliar e facilitar o acesso dos produtores ao crédito rural, Como consequência, o acordo deverá proporcionar a melhoria de renda e das condições de vida das famílias rurais atendidas na área de abrangência do banco. O banco mantém ainda parceria com empresas fornecedoras de máquinas, equipamentos e insumos agropecuários para possibilitar a modernização do setor. O Banco do Nordeste atua em estreita parceria com o Ministério da Agricultura, Pecuária e Abastecimento, apoiando os diversos programas do governo federal por meio de sua ação financiadora em consonância com as políticas públicas. É tudo isso e muito mais que faz do Banco do Nordeste o maior parceiro para acelerar o desenvolvimento do agronegócio.
Okay, welcome, good morning, everyone. We are going to start our session after some small troubles at the beginning, but we are all on track, I think, or most of us. So we're going to start this interesting session. This session name is Use of Bioclimatic Indices for Assessment of Drought and Climate Change. We have today 4 speakers. Francesca Ventura is from the University of Bologna. Donatella Spano is from the University of Sassari. And Giuseppe Passarella is from the Water Research Institute of National Research Council. And Ghaieth Ben Hamouda is from the University of Bologna. As you can see, all of them are from Italy. And myself, Octavio Lagos from the University of Concepción in Chile. So semi-arid regions in Italy, Brazil, Chile, and California are characterized by having variable meteorological conditions. And the figure in the left is showing the deficit of precipitation in Chile in 2019. So as you can see, our deficit in our country starts from 15% in the south, which is very rare, and up to 80% in the north, which is pretty extreme. So agricultural production relies primarily on water supplies to meet the water requirements. And the increase of frequency and magnitude of extreme events often call into question about the adequacy, how sufficient is the water, how flexible are the water supplies. So in this context, several climatic and environmental indices has been proposed in the literature to quantify the severity and the effect of climate change and climate variability. Some of them relies in environmental variables like precipitation, temperature, but others, bioclimatic indices, also include other information from the vegetation, for example, evapotranspiration. This is the main topic of this session, and we have 4 presentations. First, Francesca Ventura will talk about bioclimatic indices to assess drought as an introduction. Then Professor Spano is going to show the use of bioclimatic indices to assess climate change trends and impacts in the Sardinia region in Italy. Giuseppe Passarella will show aridity indices for water resource planning and management in the Puglia region, also in Italy. And Ghaieth Ben Hamouda will show preliminary assessment of bioclimatic indices in California in the Fresno County. So our first speaker, Francesca Ventura, is associate professor at the Agricultural, Environmental, Food Science and Technology of the University of Bologna. And she is president of the Italian Association of Agrometeorology and editor-in-chief of the Italian Journal of Agrometeorology. She is teaching agrometeorology, agroclimatology, and agricultural ecology in the University of Bologna. She mainly studied crop phenology, evapotranspiration from crops, modeling in the framework of climate change, and more recently, precision irrigation. So, Francesca, please, can you you can start your presentation. I will.
Okay, thank you very much, Octavio. I hope you can see my screen, my presentation.
Yeah, it's perfect.
Okay, thanks a lot. So my name is Francesca Ventura. I work at the University of Bologna in Italy. And I'm going to give you a short presentation as an introduction of what is a climatic index and what is a bioclimatic index. I show you the most popular, most used and recent indexes, bioclimatic indexes, and then I will tell you some further requirements of the research and the perspectives. So the new climate is bringing us more frequent extreme events such as drought, heat waves, floods, mild winter, and then frost waves, and so on. So these events, along with the rapid evolution of crops and new production systems, generate new irrigation demands and the need for more appropriate water management. So the use of agriculture for the irrigation, the water comes primarily from renewable freshwater resources, but also from groundwater, with often over abstraction of this groundwater, or even withdrawal from the fossil groundwater, wasting precious resources. Then also there is the direct use of agricultural drainage water, treated wastewater, and desalinated water. In this map, you can see the huge number of the water used just for irrigation. So then the rainfall is added. In semi-arid regions, such as in Italy, in the Mediterranean basin, in Brazil, California, and Chile, meteorological conditions are gradually increasing their variability. And so the irrigated agricultural production takes place mainly relying on the water that is made available to the water system from seasonal accumulation. So due to the expansion of arid and semi-arid areas, combined with population growth and the increasing conflict between agricultural and environmental water uses, irrigated agriculture has become the center of the debate on the allocation of water resources. This can have also some social sides. For example, when in Syria the aquifers became too deep and the cost of extracting the water became too high, the farmers couldn't grow food anymore, and so they fell into poverty. And from this condition began the unrest that led to the civil war that is still ongoing after 10 years. So more important topics are around the water. Right now, in most cases, the allocation of water by management consortia takes place on the basis of evaluation that were made in the past using climatic indexes that now have some limitations. They were elaborated starting from past climates. They take into account only the climate and not the plant needs, and they don't consider the ecosystem responses. So aridity indexes represent the degree of dryness of climate at a given location. And mainly they are based on a combination of means, climatological means of annual temperature and precipitation. The bioclimatic indexes are a step forward from the aridity index because they take into account not only the abiotic parameters, but also the biotic parameters of the system, soil, plant, atmosphere. The bioclimatic indexes are, again, aggregation or combination or weighted, normalized, standardized combination of meteorological variables. But they provide a synthetic indication of climate features related with plants, with the plants population, with the crop distribution and the production also. The more simple way to obtain this is to use ETO, evapotranspiration, reference evapotranspiration. Here you see a list of the many possible indexes that exist. I only will show you a few. Moreover, having reliable indexes that consider both climate and plant water needs can bring to the agroclimatic zoning or mapping. And this will help to define areas that will be suitable for a certain range of crops and cultivars, and will help to decide how manage the water allocation during the season, and how to decide the crops from one season to the other. And then reliable indexes allow the study of temporal evolution of the indexes and of the climate in the recent past, and also through projection, the evolution into the future climate, and also the analysis of scenarios. And you will see this, as you can see from this map here of Apulia, you will see some examples from the following speakers. So these are the indexes that I'm going to talk you about, some old, some very, very new, very recently developed. So starting from the history, the first one is the Marton Aridity Index. It was developed and proposed by the Marton in 1926, so it's almost a century ago. And he defined aridity categories starting from total annual precipitation and annual mean air temperature in the way you see here, and defines 7 aridity categories going from low numbers, which is an arid climate, to extremely humid with high numbers. So why? We said that the plant goes into the bioclimatic index, but here I can only see temperature and precipitation. This is because de Marton thought this index in the irrigation perspective, like we can see in this table. So in this table, we see that when the IDM is low, he suggests that there is a need of continuous irrigation. And then going up with the numbers, less needs occasional irrigation, infrequent, or even the water self-sufficiency. So the index was accompanied by irrigation suggestions. Here you can see the modified IDM in the way of we have a monthly index, and this is because, of course, you want to have crops and crops as a crop cycle. So you are interested in which is the situation, not on the whole year, but in certain period of time. And so you can calculate a monthly IDM. So this was the father of all the bioclimatic indexes. The next was developed by UNEP, so United Nations Environmental Program, in the 90s. In this case, the index defines aridity as the ratio of precipitation to reference evapotranspiration. And again, we have here a mean annual precipitation and a mean annual reference evapotranspiration. This goes from around 0 for very arid climate to up to 1 for humid climate. And here you can see a map of the index all over the world. So aridity often is thought as a high temperature and water stress, but also heat stress. This is not always true. Aridity in this case is the relationship between the water coming in, so the water supply, which is precipitation, and the water going out from the system, which is evapotranspiration. So the drying power of the atmosphere to remove the water from the system, again, the plant, soil, water system, okay? So when the potential evapotranspiration is higher than precipitation, then the climate is considered arid. And so in this map, you can see the situation worldwide. The UNEP aridity index is very simple. The next one are quite complicated. This is the self-calibrated Palmer Drought Severity Index. It was developed and proposed in 2004. And again, is a step forward because not only takes into account the monthly precipitation and evapotranspiration, but also soil water content. Soil water content is a way to assess soil moisture, which is the water that is stored in the soil and may be used from the plant, even if it's not coming in. Okay, so Palmer proposed a way, a very simple water balance model at the soil, taking into account the water coming off not only by evapotranspiration, but also by runoff or deep percolation, and assessing which is the water stored in the soil. So this is more complicated because you need to detail which kind of soil you have. So soil mapping is requested. We have here 11 classes, and going to the very wet with the positive numbers, around 0, so from -0.5, sorry, to plus 0.5, we have the near normal, whatever this means, climate, and then with the negative numbers, we have the dry climate. The next one is more complicated, and the standardized precipitation evapotranspiration index called SPEI. Here in the graph, in the image, you can see actually the wet page. This is very important because the index is complicated, but they give you all the possibility to calculate it, even the software, which is an R routine, which can be used, and again, assess the amount of water, calculating precipitation minus ETO monthly, on a monthly basis. What you can see here, I don't know if you see my mouse, in this graph here in the image with the blue and red. So the blue are the period with an excess of water, and the red are the period with a shortage of water. This means that you can actually calculate and watch the onset, the duration, and the magnitude, and the variation in time of the drought. Okay, so you can follow in the past and also make forecast in the future using forecasted data or climatic data. Okay, so this is very interesting and helps to have a drought monitoring of an area in time. This is the SPEI applied in my region. So we have a drought bulletin, and this is the calculation of the drought index for 6 months in my region. And this is a map worldwide again. You can see the classes. Again, we have positive and negative numbers for the wet or dry climate. Last but not least, this is the normalized ecosystem drought index. It's called NEDI. Is really very new. You can see here the reference. As in all the other indexes, I give you the reference that may be useful. So it was developed and published in 2018, so a couple of years ago. It was tested in California, so is very well known, but only in California, so needs to be tested somewhere else. And again, this rely on the difference between precipitation and evapotranspiration on a monthly time lag. But in this case, the precipitation is of the previous month. And then you can decide if the time lag is for 1 month, 2 months, and so on. Why? Because we can have precipitation in a period where there is no vegetation on the soil, so the soil is bare and there is a storage in the soil of water that plants may use later. So in this case, it's more dynamic. This index is more dynamic and can take into account in some way the ecosystem response to the drought. And you can see also examples and application case studies later in this roundtable. So again, this is a normalized index, which is very helpful because you can compare index results from different places in the world. But in my opinion, they only show 3 classes. This goes from -1 to +1, with the minus data that are dry climate and the plus data, positive data that are wet climate. But I think when you want to make maps of these 3 classes are not enough. There is the need of more detailed classification. But still, there is a lot to do just because it's so new. So as a short conclusion, what we learned, the increase in meteorological variability makes water management more difficult, often having to compensate for the deficiencies and excess of water in the same place within a short period of time. So the work of the water managers is really very much difficult, and they have to be supported in their taking decisions. So bioclimatic indexes better express the water need for crops, and they may help water manager decisions. Which is the best bioclimatic index, which is the one that best expresses the water needs of crops from the one that I showed. There is a necessity of more calibration, more validation of these indexes. So there is a need of more research, and there is a lot going on. Moreover, scenario analysis and future projection will be easily and successfully done when these indexes will be more solid, more tested. So the following speakers will present you some case studies applying in different bioclimatic indexes in different regions. So I give them the floor, and I thank you very much for your attention.
Thank you, Francesca, for your presentation. As I remember, please, all your questions to Francesca and also for the other speakers, use the chat section of this Zoom software, and also the other question and answer tab that is also available for you. So we are going to collect all your questions and answer your question at the end of the 4 speakers. So now our next talk is from Professor Donatella Spano. She is a full professor and scientific coordinator of the PhD program in agrometeorology and ecophysiology of agricultural and forestry ecosystem at the University of Sassari. She's, among others, senior member of the strategic committee of the Euro-Mediterranean Center of Climate Change. She is actively involved in international research activities on the assessment of climate change impact and modeling in the field of agriculture and forestry. So with this, I let you with Professor Spano for his presentation, her presentation. And give me 1 second to stop sharing my screen. Okay, so.
Okay.
You can share your screen now? Yeah.
Can you see my screen?
Yeah.
Okay.
Okay, we are ready to go. Thanks.
Okay. Thank you very much, and thanks for inviting me to this important roundtable. I thank Francesca also for giving so many information about the bioclimatic indices. So she made my talk easier. And I'm focusing on Sardinian region, but just to give, I like also to give an idea of the possible application of some analysis in other countries, in Europe in particular, where we focused most of our analysis. But first, let me point out some information, because the information we can get from agroclimatic indices or from models are useful for a different spatial and temporal scale, and for different agriculture conditions. So it depends on what we want to do. And in particular, if you think that users, in particular farmers, policymakers, researchers, have to take a decision on operational, tactical, and strategic agricultures, we can use different products from the climatic, meteorological and climatic side, like weather forecast, seasonal forecast, or climate projections. And from the research side on vegetation and agriculture, we can use simple agroclimatic indicators, or continual or more complex or complicated models like land suitability, phenological models, water models, and crop simulation models. So this is just to say that we need, when we use tools, we need to keep in mind what is the aim and what the objectives of our analysis. Just to give some information about the work we did and the possible use of agroclimatic, bioclimatic indicators or indices for assess trends due to climate change, we can say that some indices are useful, and Francesca show a long list of possible indices. We, for example, used the growing degree days and the aridity index to do some analysis for planning of adaptation policies and strategies to fight climate change. In particular, we applied these two indices in Sardinia, and using a 8-kilometer resolution regional climate model, and we used the two scenarios. One extreme scenarios, RCP 8.5, and one medium scenario, RCP 4.5. And we compare for the two future time frame, 2021, 2050, and 2041, 2070 against the baseline conditions, 1975, 2005. And here is the map of Sardinia for the growing degree days. And in the upper part, there is the medium scenarios and the extreme scenarios in the lower part of the slide. you can see how much heat the region and the vegetation and the crop can accumulate. And another map is about the total reference evapotranspiration using the same scenarios and the same future time frames against the history, and you can see that the annual reference evapotranspiration increases according to the worst scenario. Also, another view of the projected condition for Sardinia is offered by the aridity index, and even here we can see how the projects show how the aridity index can increase due to climate change. So another, and those indices, as Francesca said, were used at the annual time scale. But when we need to follow at least monthly what happened in terms of dryness, we applied the potential soil moisture deficit that can easily evaluate and can easily also can give an idea of a crop irrigation demand. As said, monthly time step water balance using precipitation and reference ETO. And you can see that when this index is calculated, is cumulated month by month to a maximum value. It can be used as agroclimatic indicator. And in this graph, we can see the ETO, the precipitation by month, and the values, the cumulative values of the potential soil moisture deficit indices. And the indices reached the maximum value when the ETO overcome the precipitation value for some months. So the application of this index, the potential soil moisture deficit indices, was applied to the Sardinia case, as well as I showed before, for the two scenarios and the two time period, future time frames. And you can see the difference in color, how the dryness can be strong and widespread in the islands. One statistical exercise we did was to try to find the linear relationship between the variation in the index and the irrigation needs, considering the data at regional level for 4 relevant crops. And here in the graphs, the dots represent each Italian region. So are 20 points, and I'm sorry, the name of the crops are in Italian, but it's fruit trees, olive trees, and vegetable, and grapevine. So, and you can see that there is a good relationship between the the irrigation, the applied irrigation, and the index. And a similar exercise we did also for the data at the province level. And again, there is a strong linear relationship between the variation of the index and the irrigation needs. So this actually we did for Sardinia, we did for all region in Italy, but also we did for Europe, and so it's a good information for that users can use for make adaptation option to climate change in their territory. Another experiment we did was using not projection but seasonal forecast, and we use agroclimatic indicators calculated using retrospective seasonal forecasts and also observational data to compare and to evaluate, to assess the accuracy of this analysis. And inside of this project called European project called Medscope, we also developed a web tool where the indices for all Europe were can easily calculate. So in the tool, user can just choose the select the indicator. It can select the area of the territory that where they want to have information, and then they can have also the accuracy of the forecast. So it's a useful tool that so far is inside of the output of the project, but can be in the near future and can be online. So from simple indicator, we can also use water models that can link agroclimatic indicator with more sophisticated information, and in particular we use the CIMATO model, that is a water balance model developed by University of California, Davis, in conjunction with the California Department of Water Resources, and our group implemented it in a platform, in GIS platform under the program to provide regional simulation of reference evapotranspiration, crop evapotranspiration, actual evapotranspiration, and net water application. And so in addition to irrigation scheduling and yield losses. So we used this model in this platform to provide regional simulation of ET and irrigation requirement for several crops under different management practices. Here, just an example of the type of maps for crop evapotranspiration and actual evapotranspiration for two scenarios with the different time frame, future time frame. And this is the expected changes in irrigation requirement for different crops in Sardinia under climate change. Sorry, again, the name of the crops are in Italian, sorry, I forgot to change it. But you can see that how can be the anomalies in irrigation requirement from in comparing to the baseline. And there is especially a higher increase in water demand for pasture, orange trees, rice, and olive trees. Also, this type of analysis was conducted to develop the Sardinia adaptation strategy that where several sectors were analyzed, but in particular the water system was included in analyzing the irrigation requirement for agriculture sector and also the increased competition between sectors. We used the IPCC approach, where when you needed to calculate the risk, you needed to know the hazard, the vulnerability, and the exposure of the territory. And in changing the climate system and development process, including adaptation and mitigation, are drivers of hazard, exposure, and vulnerability. So using this, that is called impact chain approach, we use this, and this is the link with the bioclimatic indices. We used indicators as a proxy to describe what can be the new condition for water demand in Sardinia. And so we collect the data, standardize the indicator, weighted the indicator, and then each indicator was classified in 5 classes from lower to higher level, so from optimal condition to critical conditions. And so we again used the aridity index for the 2 scenarios. We use the exposure to risk for water resources that were referred to irrigated area in the agriculture sector. For sensitivity, would refer to the loss of productivity due to water stress and depending on crop types. And at the end, we calculate for each municipality territory the effective distribution of irrigated crop present and the irrigation requirement per crop. And here are the classes of risk. And you can see that there are municipalities that fall in the highest classes, and more are characterized by winter and spring crops. So we developed actually other analysis, other indicator at different scale. In particular, we thought about agricultural district and water availability in associated reservoir as a result of climate change. So we just to mention this study because can be of some interest for some of you. And so we based on the changes in water entering reservoir, water for irrigation and evaporation losses under climate change, we developed indicators that are listed in this slide and that can be useful. Also because evaluate vulnerability of irrigating agriculture and adaptation needs, it's very important to fulfill agriculture and irrigation requirements. And this study was conducted not only in Sardinia, 3 cases in Sardinia, but also in Apulia and in Sicily. So we calculate the reservoir inflow and the reservoir water outflow, in particular the water demand and the evaporation. And 2 indices were developed to give some information exactly about how self-sufficiency in capacity demand can be a territory, and the allowable water losses for irrigation. This study was published, so if someone is interested, you can go to see the results of this study. And just to conclude, I have some concluding remark. I think that indices in conjunction with the water models can be very important for climate change trends, and also for climate services, can support adaptations, the choice of adaptation strategies and options, and also for policy. But we need also to consider that we have different information and tools that research are developing now. So we needed to put together also innovation like machine learning, artificial intelligence, early warning system, and also think that the management is very important when we need to work on management option, thinking about the sustainability of our agricultural sector, especially for water resources and the use of water in general. And also we need to plan, so we need to have based scientific plans to assess climate change into the in the agricultural sectors, and also we need to have farmers that are awareness, that are really informed, and so we needed to communicate with them. Thank you very much for your attention.
Thank you, Donatella, for your presentation, and please remember questions in the chat or also in the question and answer tab that we have available for this. The next speaker is, one second, Dr. Giuseppe Passarella. He is a civil engineer from the University of Bari. Is a researcher at the Department of Bari of the Water Research Institute of the Italian National Research Council. Since 1987, Dr. Passarella has been involved in several studies, including groundwater modeling, techniques and methods for water resource management, monitoring, and protections mainly. His research activities are in several areas related to water resources, related to groundwater modeling, groundwater protection, and water resources management, among others. So, but for today, he also will talk about the use of aridity and bioclimatic indices in arid and semi-arid areas for the drought assessment. So, Dr. Passarella, please start. So now I think you can use the share screen. Your microphone is muted, so. Giuseppe, your microphone is muted. Let's see. Now I think this.
Do you hear me?
Yeah, we can hear you. And
Okay.
can you please turn off your microphone, please? So thanks. Yeah, go ahead. Everything looks good.
Okay. Good morning, everybody. The time we are going through does not allow us to meet in person, so let me spend a few minutes to introduce me and my institute. As Octavio, the convener, has just kindly reported, my name is Giuseppe Passarella. I'm a researcher at the Water Research Institute of the Italian National Research Council. Let's describe just a few words about my institute. The headquarters of my institute is in Rome, but it includes some other departments located all over the boat, from the northern border down to the south. The Water Research Institute was established in 1968 to carry out research in management and protection of water resources and development of methods and technologies for water and wastewater treatment. Today it includes more than 200 people, of which 100 permanent and 50 temporary researchers, whose activities concern all sectors of environmental sciences and involve us in a number of frontier research projects with important institutes all over the world. Let's move to the actual presentation. During the next 20 minutes, about 20 minutes, I plan to move through the following 6 points. Point 1, background and motivation. A few slides to show the reasons that led to start studying bioclimatic indexes. Point 2, climate aridity and bioclimate indexes, to explore the apparently subtle differences between aridity indexes and bioclimatic. Point 3, Demarton's index of aridity, just to introduce among some aridity, some other aridity indexes, the one of Demarton, which is still worldwide used, even being one of the oldest indexes, and that is the index we applied in this work. Point 4, the Apulian experience. The work I'm going to present concerns the Apulia, my native region, which is located in Italy, in the southern part, and in the middle of the Mediterranean Sea. And scientific evidences show that it is progressively moving to arid conditions. Finally, point 5 and 6 concern strengths and weakness of the proposed methodologies and the future plans. As reported during the previous presentations from Francesca, in semi-arid regions of many countries such as California, Chile, and Italy, all characterized by gradually increasing variability of weather conditions, irrigation systems usually benefits from seasonal accumulation of water systems to meet the crop's need and limit the effect of weather fluctuation. In these regions, extreme weather events have been observed happening with increasing frequency and intensity. These events question the adequacy of water allocation, which is often established based on past hydrological series and climate stationary hypotheses. Then, using reliable bioclimatic information for irrigated agricultural production would allow to quantify in space and time those meteorological parameters which can influence crop water demand and water availability. Reconsider water allocation or land use plans to minimize water deficit and surplus related to water demand changes due to climate change, and suitably move water resources among hydrological basins to improve strategies to joint use of surface, for joint use of surface and groundwater. Let's now briefly have a look at the apparently subtle difference among terms as aridity, climatic, and bioclimatic. Climatology concerns the study and description of climate. In particular, applied climatology addresses the climate factor involved in problems related to the planning, design, and operation of climate sensitivity sector of modern society. Bioclimatology is a branch of climatology that deals with the effect of climate on the health and activity of human beings and on animal and plants. Concerning plants, bioclimatology deals with the interaction between climate and the distribution of plant communities in the different regions of the earth. The aridity, as told before, the aridity is the degree to which a climate lacks effective life-promoting moisture. Aridity is a climatic condition determined by the scarcity of rainfall and strong evaporation, which removes moisture from the soil. Then the aridity is a climatic characteristics resulting from frequent and long-lasting periods of drought affecting a given area. It can be structural when drought conditions are permanent, or occasional when it is associated with exceptional event of prolonged duration. The United Nations Environmental Programme certificates in the World Atlas of Desertification that about 47% of the planet's surface is characterized by arid or semi-arid or dry subhumid lands. It considers desertification as the land degradation in arid, semi-arid and dry subhumid areas resulting from climatic variation and human activities. The UNEP collectively refers to these climate classes, arid, semi-arid and dry subhumid climatic zones, which define regarding to the ratio precipitation potential evapotranspiration as susceptible drylands to soil and vegetation degradation. Finally, hyperarid zones, being the true desert, are not considered to be prone to desertification given their very low biological productivity. In the scientific literature, the usual approach to measuring the aridity prescribes to define classification index we have seen during the other presentation, calculated using long-term weather time series, such as precipitation, air temperature, wind speed, and so on. Frequently applied aridity indexes are the Thornes-White, the Demartons, and the UNEP index. As shown in the previous presentation, again, many other indexes are available in scientific literature, each having different objective, but all based on weather variables. A weak point of these indexes is that given the strong dependency of aridity indexes on time, space variable weather data, their quality depends on the number and distribution of meteorological monitoring stations over the considered area. The proposed methodology was applied to precipitation and temperature time series collected at weather stations throughout the Apulia, a coastal region of southern Italy. The main evidence of climate change in Apulia, is for Italy and Europe, are a general increase of temperatures and changes in precipitation distribution, which tend to be concentrated in time and intense. The Italian Environmental Protection Agency indicates that all the 20 Italian regions are affected by vulnerable area, but the Apulia, together with other 6 regions, overcome the national average. Inevitable consequences are the recurrent droughts, soil drying up, water resources depletion, coastal marine environment decline, and hydrogeological instability. From a hydrological standpoint, Apulia is characterized by an almost total shortage of surface water courses. 3/4 of the water for potable use comes from springs and reservoirs located outside the region. The remaining quarter comes from groundwater. The latter also supply a large part of industrial and agricultural needs, 60% of the industrial need and about 75% of the agricultural need. Well, in 2018, a research was started with the University of California, Davis to define and test a methodology for the analysis of weather data in space and time in order to access the aridity level and the water requirements at regional scale and support water resources and landscape management. This study produced the regional maps of the classified Martins index and trend assessment of this latter at each weather station, weather monitoring station. The methodology relies on a modular assembly of statistical tests and methods and uses point-scale monitored measurements of meteorological data. Once computed the aridity index at each monitoring station and for each considered year, we spatialized the median value of the time series at each station and classified the resulting maps. On the other hand, we evaluated also the temporal trends, which resulted significant in 15 cases out of the 80 considered. This is the map of the Apulia region with the 80 weather stations considered in this study. The region is characterized by a typical Mediterranean climate. The precipitation is scarce, around 400 millimeters per year on average, and the temperature is very mild overall, most of the year. Summers are long, dry, and hot. Rainfall can lack for 2 or 3 consecutive months, and temperature often exceed 40 degrees. In winter, precipitation is scarce and irregular. Temperatures are mild, usually exceeding 10 degrees. The level of aridity in this study was evaluated by the Martins index. The choice was driven by the scientific literature for Mediterranean regions, which reports a number of studies. carried out in the same climatological environment, and which use this index of aridity. The table, as seen before during the other presentation, the table on the right side of the slide shows the climatic classification proposed by Demarton based on threshold values of this index. In the table, Demarton also outlooks irrigation needs for different climatic zones. Nevertheless, this latter classification is rather qualitative, since this index doesn't include any crop or water balance data or information. This figure shows the regional map of the median values of the Demarton's index during the period 1931-2010, estimated by ordinary kriging in a 1 kilometer mesh grid. The second figure shows the previous map classified according to the scheme of the table in the previous slide. Finally, the third map shows the Demarton index spatially aggregated by municipality. This last transformation enables water and land managers to assign climatic classes to municipalities, facilitating the identification of the stakeholders to interact with for promoting and implementing actions for safeguarding natural resources while maintaining production activities. The results of the spatial analysis of the Demarton's index highlights that the Apulian territory is characterized by about 40% of dry subhumid Mediterranean and 30% of subhumid climate, which need supplementary irrigation both. For the remaining 30% of the region, 1/3 is affected by the semi-arid climate, which needs irrigation, and 2/3 have a humid climate, which needs only occasional irrigation. This figure shows the position of the 15 weather stations with a significant decreasing trend, that is towards more arid classes, according to the Mann-Kendall test with significance level 0.1. Weather stations that show faster trends to increasing aridity are those located in the Apennines and Gargano, in the northern part of the region. Nevertheless, these areas are characterized by higher altitudes with a current humid and perhumid climate due to high rainfall rates and low temperatures. Stations located in the Salento and Arco Ionico also show an increasing aridity trend, but they are more worrying because they are currently characterized by a certain level of dryness. Actions suggested in these areas can consist of careful monitoring and participatory policies on land and water uses. Let's go toward the conclusion of this presentation. We have proposed a methodology that allows obtaining information about the level of aridity of a region and its evolution with time. The Demarton's classification, even though indicating a supposed irrigation need per aridity class, is based solely on weather informations. Then, in the context of agricultural sciences, it characterized the physical environment where plant community develop and that influence this latter, but it doesn't quantify the influence of climate on processes such as crops evapotranspiration and productive response, and hydrological balance. Then the need arises to combining this climatic classification with land use, crop characteristics, and available water supply information to identify possible options to match water demand and available supply in space and time. So substantially, the need arises of using bioclimatic indexes that consider parameters linked to plants' biological processes suitable to quantify the interaction between climate and plant communities in the considered area. And this is what we are going to develop in next research activities with all the friends in this meeting. Thank you. These are my contacts if somebody is interested to contact me.
Okay, thank you so much, Giuseppe. We're gonna move now to our next guest. So our next talk is from Ghaieth Ben Hamouda. Oops, my pronunciation is okay. He holds an engineering degree in water resources and management from the University of Gendouba in Tunisia, and he has a master degree in land and water resources management from the Mediterranean Agronomic Institute of Bari in Italy. He's currently a PhD student in agricultural and food science at the University of Bologna in Italy. So please, Ghaieth, so you have the control now.
Thank you, Octavio. Just a second to share my presentation.
Yeah.
Okay. Right, great. Thank you everyone for your presence, and I would like also to thank the organizers for this interesting session. I'm just, our study is still at the beginning, so I'm gonna try to give a glimpse on the preliminary results that we got for the assessment of bioclimatic indices in Fresno County, California. So as the previous presenter said already, globally climate change has been increasing frequency and magnitude of extreme weather events. For example, droughts, heat spells, warmer winter temperatures, and especially in arid and semi-arid regions. At least in the last 50 years, we have seen a lot of alarming examples of the consequences of these changes. For example, the increased snow melt in the Andes Mountains in Chile, or increased from 2014 to 2017. And coming to agriculture, if we add also the fast evolution of crops, farming systems, irrigation practices, all of these are putting a lot of pressure on irrigation water demands and future water availability, as I said before, particularly in arid and semi-arid regions, where it's almost impossible to grow crops without irrigation. So in that purpose, many climatic indices have been developed to try to understand and describe how the climate change is impacting the agricultural water resources. However, most of these climatic indices, have been developed mostly for dry land or rain-fed agriculture, relying for their calculation mainly on either air temperature or precipitation, or sometimes a combination of both as well, without considering the specific water needs of irrigated crops and irrigation methods used by farmers. So basically, climatic indices do not account for variables that are fully or partially related to biological processes, and mainly here I'm talking about crop evapotranspiration. This is why many of these climatic indices, they actually fail to represent the real situation on the ground when it comes to water distribution and water availability. So on the other hand, bioclimatic indices, they should give better answers to this kind of matters, because the bioclimatic indices, they help interpreting physical phenomena linked to the biological processes in progress. For example, surface runoff or soil infiltration, the water table level. So when you use bioclimatic indices, you can assess the spatial distribution and temporal evolution of climatic parameters that could affect water supply for agricultural production. You can also adjust water allocation plans to minimize water supply deficit and excess, of course, relative to water and climate change in climate change conditions. Also, you can give a more accurate and realistic information for water transfers among watersheds or groundwater and basins. So the objectives of this study and the bigger projects that we just started, as I said before, is to advocate the use of bioclimatic indices for crop water demand studies and irrigation management, then evaluate bioclimatic information in space and time to define bioclimatic zones and to provide consistent information on moisture or dryness level of irrigated lands. Then we have also this project is also aimed to, we can use bioclimatic information to support water planning, allocation, management decisions for irrigated areas, especially those that with water constraints and environmental sustainability problems. This case study is a part of a bigger project, is a continuation of the work done by Dr. Passarella that he just spoke about. The project is about use of bioclimatic indices to estimate the effects of drought and climate change. It's led by the University of California, Davis, with 3 partners from Brazil, Chile, and Italy. For this case study, the area we chose is the Fresno County in Central California. This county is has a very important agricultural production in California, state of California, and also in the whole United States. It has an area of almost 1.5, around 1.5 million hectares. And the data available in this county come mostly from 12 active weather stations from the California Irrigation Management System, and 10 weather stations from the US National Climatic Data Center, the NCDC. But as you can see on the map, these weather stations, they don't have they're not evenly distributed, so they don't give a good spatial representation of the area. So we chose instead to use data points from PRISM model on their 4x4 kilometer grid. Of course, these data from PRISM have been compared against the weather measurements, and they gave good correlation. So data in themselves, they are on a daily scale. So we have precipitation, we have temperature, reference evapotranspiration, effective precipitation, and evapotranspiration of applied water, which is the net irrigation, water irrigation, or also the fraction of applied water that contributes to crop evapotranspiration. So the data, as I said before, it's precipitation and the air temperature from the PRISM model for the period 1981 and 2015. So it's 34 years of data. And then we have the ETO, the ET of applied water and effective precipitation. They are generated for the same period using the CalCimetao model. Then these data were aggregated on a monthly, annual, and seasonal, and by seasonal I mean the irrigation season, then non-seasonal scale or off-season scale, including also the high peak and the low peak months during the irrigation season, and these are determined using the ET of applied water. As the previous speakers also said, that there are a lot of many climatic or many indices in general that are used in the literature for to assess either the dryness or the aridity of a certain area. So according to the literature, those are the 5 let's say we chose four bioclimatic indices that are mostly used according to what we saw, at least in the literature. So we have the Di-Martoni index, already introduced by the previous speakers. We have the UNEP aridity index, the SCPDSI as a calibrated form of the PDSI index, and also the SPEI. And we chose to include the NEDI that already Professor Ventura talked about. It's a new, relatively new index developed by Shang et al. In California. Has been tested, I think, twice till now. I saw 2 papers using NEDI already, but still has to be further tested. So many of these indices, they obviously have different classification scales, so it's a bit difficult to compare between them. So we chose to use a control variable against which they can be compared. In this case, the ET of applied water. Also, using ET of applied water as a control variable allows to know which of these indices can give a good idea of the irrigation water demand in the area and its evolution over time. And these are the preliminary results, let's say the first results that we got. So basically, because we don't know the land use over time, at least in Fresno County, we chose the crop to be irrigated grass, and we assume that it's homogeneously spread throughout the region. Then we chose 2 variation of precipitation for the calculation. So we have the normal precipitation and effective precipitation in this case, and in all the cases of the calculations of all the indices. The scales that we have for now are annual, on season, and on season are from April to September, and then the off season. So as you can see here, and you can see also in all the indices, when you use effective precipitations, you have a better regression with ETAW, so a higher R-square values. This goes the same for also, also the UN aridity index, the SCPDSI, and the SPEI. And when it comes to NEDI, NEDI actually gave the higher, let's say the best regression with ETAW, the higher R-square, especially when you use effective precipitation. So as I said, these are just a glimpse, like still a first results that we got. Still the study is still longer. Still a lot of things that needs to be done. I will talk about them at the end. So to summarize or to conclude what we saw so far, at least from these first results, we have, so the data obtained from PRISM that we used for this study have good correlation with CIMIS and NCDC weather stations, so they were safe to use. This is the first point. The second point, so in this first assessment, let's say we used 5 bioclimatic indices. So the Marton, the UNEP, the CPDSI, the SPEI, and the NEDI, and then they were calculated using meteorological data. And then we used both a variation of precipitation, so we used normal and effective precipitation for the calculation. Then, obviously, as you said, as you've seen before, so the NEDI bioclimatic index so far had the highest correlation with the control variable ET of applied water. And so generally the use of the effective precipitation in all indices improves the correlation of all the indices with the selected control variable, which is ETAW, as we said before. Now, what is intended to be done in the future, the continuation of this work, so we'll have to divide the area of interest into low demand, medium, and high irrigation water demand zones using ETAW. That's the first step. Then we have to identify possible fluctuations of the seasonal irrigation water demand, as well as a potential shift in the precipitation month and their effect of the spatial distribution of bioclimatic zones over time. And then evaluate the performance of the different bioclimatic indices in describing irrigation water demand patterns and trends. So that's it. That's for at least for this first assessment. Before ending, I would like to give a special thanks to Dr. Morteza Orang from the California Department of Water Resources, and Dr. Mahesh Masti from University of Merced for their precious contribution to the data elaboration. Thank you for your attention. I've been a bit fast. I hope it's not too fast. And if you have any questions, please feel free to ask. Yeah, thank you very much.
Thank you, Ghaieth, for your presentation. I think we have plenty of time. We have 25 minutes, I think, for questions. So I collect some questions that the audience ask. I quickly put it on the PowerPoint. So there are some for each of you. So first of all, there are two questions related to the presentation of Francesca and Donatella. The first one is the UNEP added index considers the raw rainfall, but not the runoff, correct? In other terms, the index does not consider the regulation capacity of the land to the rain, but only the total rainfall. So it is pretty inaccurate. Could Francesca and Donatella elaborate a bit on that? So, Francesca?
Yes, it's exactly true. The observation is true. So it's pretty not very elaborate, not very detailed. Is a rough index. It was the first one. As you can see, it's used at a world-wide scale. So that's why it's still used. You can look in the net and find the Drought World Atlas or Aridity World Atlas, which is starts from the elaboration of this index. And so that's why we need to go forward from this, which is very simple, but not accurate enough. Something that I want to say about being accurate or not is, I'm not sure if some of us spoke about how to calculate ETO. I mean, there are several possible equations going from the very accurate Penman-Monteith up to the or down to the very not accurate climatologic Thorndike. Thorndike is the equation that was used by Demarton when he elaborated his index, and I think works starting from a monthly average temperature and monthly average temperature only. So it's pretty inaccurate. It's climatological. So the monthly average temperature is climatological. And but someone checked the differences in using the very accurate and the very inaccurate. And the error is so small that from a climatological point of view, it doesn't make sense. So you can choose to use whichever ETO equation or whichever ETO data you already have. And this is speaking about inaccurate, yes, depends on the level, the scale. Okay, I hope I answered the question.
Mm-hmm. Donatella, yes. You want to add?
Yeah, I agree with Francesca, but as I said, commenting one of my first slides, I think that accuracy in this topic depends also on the objective, on the aim of the use of the bioclimatic index. So if it's for scheduling, irrigation scheduling, it's one thing. It's for just to have an idea of dryness, it's another thing. So I think that we cannot give an absolute information and exact information about the accuracy, but we need to elaborate a more complex answer. Depends on, as I said, depends on the objective of the use of these indices.
Mm-hmm. Okay. A second question from Gustavo Lira. He said, note a phase delay between the physical indices like SPI, PDSI, SPIE, to characterize drought and vegetation. Thus, what is the ideal time scale for the application of bioclimatic indices, in your opinion, Donatella?
Actually, I didn't use all of these, so maybe Francesca and Giuseppe that they use these indexes can give some more detailed answer. But it's clear that there is a difference in response between the physical and the biotic system, and that this can be, if we use more sophisticated models that are physiological based, this can be in some way solved. So we need to consider that the index have some limitation, and we know that.
Mm-hmm. Okay, Francesca, your microphone is muted.
Yes, well, indexes are just indexes. They give an idea, no? So, okay. I'm not sure about which is the ideal time scale of the application. It depends again on what you are going to. Maybe the work that is Ghaieth Ben Hamouda is doing, so going into such a detail and the comparison of different index in such a kind of a wide area, but of course it's a region, so it's well known. This will help us to answer these questions. I don't know if Ghaieth wants to say something.
I can, just one more comment. I can say that in any case, I don't know if there is an ideal time scale, because you can apply the bioclimatic index using different physical information, so weather or climate. So you can do the analysis. As I said, there is a chain, the objective, and then the information you have, and how the information you have are accurate in terms of weather forecast, seasonal forecast, or projections, and then the bioclimatic indices provides information that are limited by the structure of the index, the elements that includes in the index. So there are different ingredients that may make an index accurate, and that affect the time scale.
Can I say that I completely agree with what said till now? I mean, it doesn't exist an ideal time scale for the application of bioclimatic index. It depends on the objectives you have, the aim of the application of the use of the climatic and bioclimatic indexes, and on the time scale of the information you can use, which is also important. These are just simple models, I mean, so that they work if your information, your data are reliable, and if you don't have enough information, the models doesn't work. So it depends. It depends on what you want to know from these models, and what is the database you are using to make them work, I mean.
Yeah, I can add something. No, if you can, Octavio. So, for example, most of these indices, they've been developed for a monthly scale and tested on a monthly scale in many places. But still, I mean, they thought the monthly scale would be perfect, the best.
We lost you. I lost everyone, or only Gate?
No, I think it's only him that got
The connection.
Yeah, the connection.
Yes.
Yeah, let's see if he can come back. I can. Well, he's coming back. I can say that we use these indexes. Rick said it seems that session was cut off.
Oh.
Sure. Let's see that first. So, no, I think we're okay.
No, we're still on.
Yeah,
We're still on and it's still recording.
Yeah. So one thing that I can add is that we use those indexes here in one region in the middle valley of Chile, and I think the ideal time scale depends on the goal that you want to answer, Gustavo, and also I think it's locally, because here in Chile, for example, we have precipitations during September and October that define the stage or how well water are going to be the vegetation during the summer. So if that vegetation is going to be rain-fed or irrigated, also that makes a big difference. So I think the time scale is locally and also depends on what is
Octavio, do you hear me?
Hmm?
Sorry, do you hear me, Octavio?
Yeah, I can hear you now.
Okay, sorry, the internet disconnected.
Yeah, sorry, you went out, so you can continue.
I'm saying like I know at least for the PDSI for the PDSI over 12 months. If you want to describe over 12 months of drought, is going to be a bit hard. It starts to give not very accurate results. A lot of extreme results as well. So it's preferably you don't do more than 12 months, for example, for PDSI. For SPEI, it's better. You can at least go through even for three years of drought. This is the information I know. But mostly, as I said before, it depends on where do you want to apply it, how do you want to apply it, what do you want to do with it. So it's really variable. Some index can work in some place, cannot work in another place. That's why a lot of climatic indices exist in the first place, because people are trying to adapt some of the indices to their local or regional situation. About the second question, if there is an index that considers physical and biotic indicators, I cannot really answer that question because there are so many indices. I mean, even this week I've seen at least 3 or 4 new indices in the literature. So that could be maybe there are some other indices around that actually answer that question. So yes, I mean, yeah, I hope I answered a little part of this question.
I think it's a nice question. So yeah, it's nice to talk about those things. Thanks, Gustavo, for that question. And we have more for Donatella talk about forecast. So, which are, I think, a good idea to give the bioclimatic indices a prospective character. So the question is, what time scale will be still good for the forecast, not to lose accuracy and dependability? And the 4 ones also is related, Donatella. If you see, have you checked how the forecasts were accurate against the real ground measurements? So both are related, I think.
Okay. Actually, if they are talking, the question was about seasonal forecast. I can say that there is a group in CMCC that is the Euro-Mediterranean Center on Climate Change Foundation, and they are working on seasonal forecast. They are working in a project with several others groups in Europe and actually in the world. So they are. We know that the seasonal forecasts have several limitations, and we need more research for increasing the accuracy. But in the last years, there were much better information, and also to develop climate service. That is a big thing now. To develop climate services, the weather forecasts are really important for predicting or forecast water demand for fire, for example, and etc. So about the time scale so far is 1 degree. So it's, I think it's about 120 kilometers. So it's clearly it's useful for not for small or very small local study, but it's still important. And then yes, about the forecast and the against the measurements, real ground measurements. They were tested. I don't have many details on it, but they were tested with historical data.
Okay, I think with that we can pass to the next one. So this is a question to Giuseppe from Daniele. So can you please elaborate a little bit on the limitation of the Martone index for water management purposes? He meant that the Martone index is probably good for climate characterization, so can help identifying the areas where problems are occurring or likely to occur.
Well, I guess that the Martone index is a good index in any way. It is one of the probably the oldest index used all over the world, and again, it depends. I guess it depends on the goal you have when you choose an aridity index. If you want to, or you need to just to classify your the area you are considering, usually this index is applied from regional to national scale. I guess it can give good information about the status of the things. This is obviously a descriptive model and not a forecasting model, so you can some way understand what's going on at the moment you apply your index. Not anymore, obviously, but I guess it can help the water managers over the territory in order to just define some plan for water related issues, territorial issues. I mean, I don't know. Daniele, want to add something to the discussion?
No, really. I think you nailed the main concept that it's a really a good index as a first snapshot, but then probably needs more quantitative analysis for indicating what is happening and how can manager adapt or mitigate or find way to strategize for managing resources. But I think you basically nailed the real advantages and problems.
The strong point of this index is that it's very, very simple to be applied, since it needs just precipitation and temperature values, which are usually available everywhere over the globe. I mean, so this is a good point. I mean, it's a strong point. Obviously, if you want to evaluate some more detailed information, you probably have to move to some other indicator, I mean, index.
Okay, so there is another question, I think it's for Ghaieth, but also maybe Francesca or Giuseppe can also comment on that. Is what are the advantage and disadvantage of the NEDI index? And so Ghaieth, I think I cannot connect your camera, but I think you are there, right?
Yeah, I'm here. I don't know why the camera doesn't work. I sent a message just to fix it.
Yeah, I don't have the power to activate your camera, but
okay, no worry, Octavio. It's fine. Now, for the NEDI, as I said, it's still new, so we still have to test it to see how it actually works over time, to see how does it really reflect the fluctuation and the ET of applied water, and does it really reflect the peak month variation and all of these things. But maybe I would say the NEDI at least accounts for, it has this the legacy effect on precipitation, which means it accounts for the precipitation of the previous months. So when you use it, you build some kind of time series, continuous time series on how the water availability is building up. For me, at least, I think this is the main, because it's very close to SPEI. So this is the main difference with the SPEI, at least. So it could be an advantage. We have to check. We have to still continue the work and still see how this variation in the equation, if it's really something valuable that the authors added. So even in the two other papers I saw, I can actually share them if anybody is interested. They didn't actually go much inside. They found very good results with NEDI, excellent results actually, but they didn't actually mention many disadvantage or something like that. I have to check. I have to check this information. If someone maybe is interested, you can still write me an email, and we can stay in touch and send them maybe a more detailed response, I would say.
Mm-hmm.
I guess that again the importance, it is important to understand what's your database. I mean, the NEDI index is a optimum index, maybe one of the best index in scientific literature. Anyway, it requires accurate and reliable data. The difference, I mean, going back to the previous question, the difference between the Demarton index and the NEDI index is the same between a bicycle and a Ferrari car. Maybe if you have a Ferrari, you can go fast, but you need gas and a driving license. Using the bicycle, you don't need these issues, these things. I mean, so you probably will go sure to the end of your path. I mean.
If I can comment, I think the NEDI as the one specific feature that add a lot of value And so you can quantify the ecosystem response to the climatic parameters. And so it's in this respect, is really a dynamic type of index. So it's not only evaluating or helping classifying, but also is helping manager to see how the ecosystem, whatever it is, if it's an agricultural ecosystem or is a natural vegetation ecosystem, responds to the biotic and abiotic parameters. And so this is something that was not really deployed so much in our analysis because we had a first assessment of the NADI, but I think it will be very very important in the future analysis for you know, the purposes of irrigation water management. And I think just a few indices that I've seen are have this kind of dynamic and non-static features.
Okay. So more questions.
Daniel, okay.
So we have 5 more minutes. So and we have like more questions at the time. So let's move a little bit so we can answer a question from the audience. So Donatella, most of the damages in agricultural production are due to extreme events, such as heat waves, wind, a storm, frost, etc. Can the vulnerability indicators oh, sorry,
talking about
for this extreme or only for prolonged water shortage or sustained high temperatures? I don't understand really well the questions.
Okay, I can just say that when we did the study to develop the adaptation strategy for Sardinia, but we did it also for Italy, we used different indicators, considering also the extreme events. Actually, we considered some more clearly more climatic indicators, like the number of days that are with the temperature higher than 30 degrees. So how it changes in the projection comparing to the baseline, sorry, and so all the number of days without rainfall, or the opposite, the number of consecutive rain, because we need to consider also flood. So we have the extreme events can be also the opposite one of each other. And so to the territorial analysis, considering adaptation option, possible adaptation options, we need to have we need information on extreme events, and we need to use this information into simple indicators. So it's a this question is appropriate when we talk about agricultural production, because for the agricultural systems, the extreme events are very, very, very important.
Donatella, also these two next questions from Almiro and Eusimio ask about ET, and they say how the ET was calculated in your area, and is there the need of local calibration? And the second one from Eusimio said TSSDC looks very interesting. Does this index consider irrigation efficiency and evaporative losses from reservoirs?
Okay, because I showed some projection. The projections are from from a model, as clearly. So climatic projection, we used the climatic projection to calculate ETO. And clearly the climatic projection were calibrated, were validated using local weather local data. And and the ETO was calculated using permanent or Ghaieth. It depends on the availability of the data. And in general, we used for ETO and for all the other ETC, ETA, etc. We used the CIMETO model. And so clearly also the CIMETO model in the GIS platform was used with weather forecast or with projections. It depends on clearly what was the input and the objective. There was another about the other indices, the TSSDC. Oh yes, this consider irrigation efficiency and evaporative losses because it's still based on the CIMETO GIS platform, and so the accuracy and the irrigation efficiency is considered.
All right, I think we are just on time for, I think this is gonna be the last question for all of you. It's from Mahesh Maske. This is, since most of the indices has no physical units, and most of them are normalized quantities, so how we can introduce runoff or groundwater components? Any comments?
Depends on the index.
Yeah.
The units, well, this kind of indexes, let's say, has no units. We can have precipitation in millimeters divided by temperature in Celsius. So no, it has no sense from the physical point of view. It's just an index. It's something that was invented in that way and then calibrated and works in that way. So the same is for the runoff and water content was the other quantity. Groundwater. So it comes probably with its own unit, I think. And then let's read carefully the instruction for the index.
I guess that obviously depends on the index, but groundwater and runoff are two terms related to the water balance. So given that all the bioclimatic and climatic indexes concern with precipitation at least, or evapotranspiration or evaporation, I guess these terms, groundwater not, because I guess we had to talk about infiltration instead of groundwater. And, in terms of the water balance that could be introduced instead of the term precipitation, which is just a positive term for the water balance. We use precipitation as a positive term, and evapotranspiration and evaporation as a negative term. Maybe we can use, we can introduce in this connection, or even the infiltration and runoff, but I have no idea on how to do it in terms of a formula, I mean.
Okay, thank you so much. I think the organizers are asking us to finish this session. We have more questions. We have more questions. There are a lot of congratulations to your presentations for Donatella, Francesca, Giuseppe, Ghaieth. So thank you so much for your presentations and for the answer of the question the audience asked us. So with this, we're gonna finish this. I want to say that thank you, the organizers. Thank you, Silvio, again, to give us the opportunity to give this session. Also, Daniele Zaccaria from UC Davis is responsible from this. He's who organized in the background the group that we are working on a research project about bioclimatic indexes in this semi-arid area. So if Daniele wants to say a few words, please, because the Eusimius is killing me here.
Very few words. I think it was a very interesting session because he had the theory, the science, and the applied applications and the examples. So I think we feel that we are on a right track to continue this research, and let's see what we can produce in the future. And thank you all for your effort and for the time you took for putting together your presentation and for participating and contributing to Inovagri. Thank you all.
Thank you.
Thank you very much for this.
Thank you for inviting us.
Thank you.
Thank you for the invitation.
Thank you, everyone.
And see you soon.
See you soon.
Ciao.